Hello everyone, in this video we will solve 2017 question paper for UGC NET Computer Science discipline. And if you want to download the presentation that is used in this video, then you can visit our website www.digimento.com, and over there you can go to the download section. From the download section you can download the presentation PPTs for this video, as well as you can also download the previous year UGC NET question papers. If you want to take the course for UGC NET Computer Science or UGC NET Electronics Science, then you can visit our course section to get the fees details and to take the courses. Or you can also call us on the contact numbers provided above. So without any further delay, let us just start solving the question paper of 2017 UGC NET. I hope that this video will be very helpful for you, and this will help you in your UGC NET exam preparation. For the complete video lectures, you can visit our website, and this video is available for each and every one of you. So let us start.
Hello everyone, welcome to the gatelectures.com. So in today's session, I'm going to solve UGC NET previous year question paper, which is 2017 paper 2, right? So now let's start. So the question number 1 is, consider a sequence f00 defined S. So this is any sequence, then f of 0 is equal to 1 and f of 1 is value is 1. So it is given there. Okay, this part is given. Now f of n value is this, right? And for n should be greater than or equal to 2. Then what shall be the set of values of the sequence f00? Okay, so you know the value of f0, you know the value of f1, and n should be greater than or equal to 2, right? So for that, put the values which is greater than or equal to 2 in this whole sequence equation, right? Now if we take n value is equal to 2, because n is here greater than or equal to 2, then if f of 2 is equal to this, so put n value 2 in this whole function. So this is 10 into f of n minus 1 means 2 minus 1, so this is 1. Okay, now this is plus 100 and f00, now n minus 2, so n value is in this case is 2, so 2 minus 2 is 0. Okay, and we know the value of f of 1 and f of 0, so this is 10 multiply and this value is 1, so 1 plus 100, and this is f of 0 is equal to 1, so this is 10 plus 100 is equal to 110, right? Now take n value is like 2, 3, 4, 5 and 6 and all, right? Now take the value of f of 0 is 3. Now put on the value of n is 3 in this, so 10 into f of 0 is equal to f of this is n minus 1 means 3 minus 1, so this is 2, and plus 100, and this function f is equal this is n value is 3, so 3 minus 2 is 1. Now the value is, if we calculate this 10 into, and we already calculate f of 2, so f of 2 is 110 plus 100, and we know this value is equal to 1, right? Now 1, so this will be equal to, now this is 1, 1, 0 and 0 plus 100, right? So what will be the answer? 0, 0, 2 and 1. Okay, so 1200 is the answer. Now take the value of f of 4, right? Now 10 into, put n value is 4 in this, so 4 minus 1 is 3, 3 plus 100, and this one is 3, this is 4 in this case, so 4 minus 2 is 2, and this will be this is f of 3, right? So this is f of 3. Now we know the value of f of 3 is 1200. So 10 into 1200 plus 100 divide f of 2 is 110. So this is equal to, now this will be 12,000 plus 100 and divide 110. So after calculate this whole, we get 110. Okay. Now you see the pattern. Let's see f of 5 also, right? After that we will see the pattern of the all the outputs, and then we calculate, then we conclude the set of values of the sequence f of f00, right? Now put 5 in this n. So 10 into n minus 1 is 4, 5 minus 1 is 4 plus 100 and f00 n minus 2. 5 minus 2 is 3. You know the value of f of 4 is 110 plus 100 and f of 3 value is 1200. So solve this and you got, so this is 1100 plus 100 and this is 1200. Now this is 00, 1 or 1, 2. So the value is 1. Okay. Now see the pattern. F of 0 is 1. F of 1 is 1. F of 2 is 110. F of 3 is 1200. F of 4 is again 110. Then F of 5 is 1. It means you can easily see that the set of values of the sequence F00 are like 1, then 110, then 1200, then 110 again, then 1. So it means the output are coming around only these values, these 5 values, 1, 2, 3, 4, only 4 values, because 1 is again repeated, 110 is again repeated. So 3 values are here, 1, 110 and 1200, right? So the correct answer is option 1 is the correct answer. Question number 2 is match the following. List 1 and list 2 is here. So in the list 1 some words are there, and in the list 2 the meaning of these words are available, right? And this is just a vocabulary type question, and just match with the meanings. Ambiguous means capable of more than one interpretation or meaning. Absurd mean is something which is inappropriate, illogical, and very clearly impossible, being contrary to some evident truth. And just like conjecture is just opinion, preferably based on some experience or wisdom. So they are just the meaning of this word, so you can do yourself. There's nothing to explain here. So option 1 is the right answer. Question number 3 is the function mapping R into R is defined as, right? So this is fx, this is gx, and this one is hx. Find the value of the following composite functions. So first h of gx, and the next is h of g of fx. So first find this one. So this is h of g of x. Sorry. Now is equal to h of gx is equal to 1 by x square plus 1, and h of x is x power 4. It means for this x value is this. So x, just write x and then whole power 4. Okay, so how are you going to write it? If you take this term in numerator, then the power will be minus 4. Okay, so you reverse it, then the power will be minus 4. So the first h of g of x is this one, and now calculate this h of g of fx. So first write like this. So fx value is x cube minus 4x, x cube minus 4x, and now you know that g of x value is equal to 1 by x square plus 1. So for this is the x for g. Now h of, so g value is 1 by x value is x cube minus 4x, x cube minus 4x whole square plus 1. Right? Now h of x, sorry, this is not here. So now the hx is x power 4. So for x value is this. Now write it down first, x value. So the x value is x cube minus 4x whole square plus 1 and the power is 4. Now I want this term in numerator, then write it down, but now the power is minus 4. So this is the answer for this, and this is h of gx is answer is this. Now find it out. X square plus 1 minus 4. Yes, in option 3 and option 4 this is available. Now x square minus 4, x square plus 1, but the power is minus 4 because I want this term in numerator according to the question. So option 4 is the correct answer. Okay. Now question number 4 is, how many multiples of 6 are there between the following pairs of numbers 0 and 100 and minus 6 and 34. So you have to find out the multiple of 6. According to me, you can solve this question manually because they are not giving you such a huge range. So 0 to 100 you can easily find out the number of multiples of 6. So this will be easy for you. So now write it down, all the multiples of 6. So first is 0. 0 is a multiple. Now the 6 is multiple in the range of 0 to 100. Now the next one is 12, 18, 24, 30, 36, 42, 48, 54, 60. Now the next one is 66 and 72, 78, 84, 90, and the next one is 96. So these are the multiples which is in the range of 0 to 100, right? Multiple of 6. Now count, let's do this also, in the range of minus 6 to 34, right? So minus 6 is the one which is a multiple of 6. Now the next one is 0, next 6, then 12, then 18, then 24, then 30, and stop, because I want the numbers which is multiple of 6 and is in the range of minus 6 to 34. Now count the numbers. How many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 and 17. 70 numbers which is multiple of 6 is in the range of 0 and 100, and this is 1, 2, 3, 4, 5, 6, 7, and 7 is the number of numbers are there which is a multiple of 6 is in the range of minus 6 to 34. So correct answer is 17 and 7. So third is the correct answer. Question number 5 is, consider a Hamiltonian graph G with no loops or parallel edges, and the vertex number of vertex in the graph should be greater than or equal to 3. Then which one of the following condition is true? Right? You know that the Hamiltonian if there is one graph and for Hamiltonian graph you have to cover each vertex in the graph, but nothing get repeated. Nothing, it means that no vertex should be repeated while traverse the whole graph, and there is one condition, you have to cover all the vertex in the graph. And any graph is a Hamiltonian graph only when the number of vertex should be greater than or equal to 3. This is given. And what are the more conditions are there, so that we get to know that yes, this graph is the Hamiltonian graph. So for that, if in the any graph, right, the degree of the vertex is greater than or equal to n by 2 for each vertex v. So first thing I want to tell you that they are the sufficient conditions, and this condition name is Dirac's theorem. So according to the Dirac's theorem, it states that the minimum degree of a vortex, the minimum degree of any vortex should be greater than or equal to n by 2. Means if the number of vortex in any graph, like let's suppose 4, then 4 by 2 is 2. So every vertex which is present in the graph, the minimum degree should be greater than or equal to 2, either 2, 3, 4, 5, 6. So this is according to the Dirac's theorem, we can say that yes, this condition holds true. The degree of any vortex should be greater than or equal to n by 2 for each vertex v. Now the next condition is this number of edges should be greater than or equal to 1 by 2 n minus 1 n minus 2 plus 2. Yes, put any value in the, if you can say that if with the help of, let's suppose first discuss third condition, right? So the third condition states that degree v plus degree w and it should be greater than n whenever v and w are not connected by any edge. It means that there is v vertex and there is w vertex, and they are not, you can say they are not adjacent to each other, because they say that no edge is between these two vertex. So it means that yes, they are the adjacent vertex. So according to the Oates theorem, right? According to the Oates theorem, if we see the degree of any two adjacent vertex, and we take the sum of these two non-adjacent vertex, then it will be greater than or equal to number of vertex in the graph. Yes, Oates theorem states this condition, right? If this condition holds true for any graph, we can say that yes, this is the Hamiltonian graph, right? If you see these two, with the help of these two conditions, you conclude that this is a Hamiltonian graph, then just put the values of n is here, and you can see that the number of edges will hold this condition. So this condition is always hold for the Hamiltonian graph. So second condition is also holds true. So option 4, all of the above condition are holds true for the Hamiltonian graph. Now question number 6 is, in a propositional logic, if first premise is P implies Q and R implies S, and the next one is P or R, so what will be the output? Now if you know the properties like constructive dilemma, according to the constructive dilemma, so if this is the first premise and this one is the second premise, you can easily say that Q or S is the output for these two premises, right? If we add these two premises, we get this one. And you can also see that this is P implies Q means negation of P or Q, and this is negation of R or S, and this is the AND operation between these two premises. So this is AND, and this one is P or R, right? So this is negation of P and this is P, right? 1. So this is you can say that this is P R. So this is negation of R, this is R, so this is 1. So now this Q and S is left out, so the answer is Q or S. Okay, so correct answer is option 4. Now question number 7 is, ECL is the fastest of all logic families. High speed in ECL is possible because transistors are used in different amplifier configuration in which they are never driven into. First one is race condition, second one is saturation, third one is delay, and the fourth one is high impedance. So ECL stands for emitted couple logic, is the fastest of all the logic families, and basically it is used in the applications where we need the high speed, right? So the high speed in ECL is because it is, it's already given in the question that the high speed of ECL is possible because the transistors which we used in the logic are used in different amplifier configurations in which they are never driven into the saturation. And that's why we don't need to, this ECL will not take any storage time. and due to the this property, that's why this logic is very fast in speed. So saturation is the correct option for this. Now the question number 8. A binary 3-bit down counter uses JK flip-flop with input JI, KI and the output QI, and the output is 0, 1, 2 respectively. The minimized expression for the input from following is what? So in the question, it is given that this is a 3-bit down counter. So with the help of this information, you can derive that number of flip-flops you are going to use is 3, and number of states in this is 2 raised to power n. N is 3, so this is 8. So if 8 are the states, so the maximum count will be 0 to 7. So this is number of states are, so 2 raised to power 3 minus 1. So 3 are the flip-flops, or you can say 3-bit down counter it is. So 2 raised to power 3 minus 1 is 7. Or you can say if the number of states are 8, then maximum count would be 0 to 7. Right. So these are the conditions, or you can say these are the some things which we are going to derive with this information, right? And now, so this is a down counter. So first we write it down the state diagram, right? So first step is you have to draw the state diagram, and then we write it down because we are using the JK flip-flop, then we write it down the excitation temp table, and with the help of this state table, and we redraw the table, and then we are able to draw the 3-bit down counter, synchronous counter, right? So you have to find out the you can say that you have to find out the inputs which we will give it to the JK flip-flop, so that the output would be 0, 1, 2, 3 like this. So this is our task. We have to find out the inputs we are going to give to the JK flip-flops. 3-bit JK flip-flop means we are using the 3 JK flip-flops, and they are asking you have to tell that what are the inputs you give to your JK flip-flop, so that the output would be 0, 1, 2, 3 and so on. Or in this question they are just asking 0, 1 and 2, right? So first step is draw the state diagram. So the first step is state diagram. So it means that it is a down counter. So maximum count is like this. Start from here. You know that this is 0, 0, 0. Maximum count is 0 to 7. Na? So just write it down. 1, 0, 1, 2, 3, 4, 5, 6 and 7. So how are you going to write it down? With the help of 3-bit. So this is 0, 0, 1. This is 0, 1, 0. And this will be 0, 1, 1, 1, 0, 0, 1, 0, 1. And this is 4, 2, 6, 0, and this is 1, 1. Because this is a down counting, so we start from the 7, then we go to the 1, 1, 0 state like this. So this is a down counter, so it goes like this. So 1 state say it goes to 1, 1, 0 state. The next state will be 1, 0, 1, 1, 0, 1. Next state 1, 0, 0, 1, 0, 0. Now the next state is 0, 1, 1, 0, 1, 1. Now next is 0, 1, 0, 0, 1, 0. The next is 0, 0, 1, 0, 0, 1. And the next one is 0, 0, 0 and 0, 0, 0, because the counters again come back to this state, right? Now if I draw the previous state and the next state table, so this is the previous state and the next state table. Next state. Now write it down. If my previous state is 1, 1, 1, The next state is 110. Why I'm going, from here to here? Because it's a down counter. It's count like this. If it is given that it is a up counter, then I start from here to here, from top to bottom. So it counts like 7, 6, 5, 4, 3, 2, 1. That's why I go like this. So this is 7 and the next state is 6. So 6 is 110, right? If I'm here 110, if I'm at state 6, then I'll go to the 5, 1, 0, 1. If I'm at state 5, then I'm going to state at 4. If I'm at state 4, then I'm going to state at 3. If this is 0, 1, 1, if I'm at state 3, then I'll go to the state 2. And if I'm at state 2, then I'm going to state at 1. And if I'm at state 1, then I'm going to state 0, 0, 0. And if I'm at state 0, then it goes to state 7. So this is 1, 1, 1. So this is your first step. So first step is, one second, I'm just highlighting the first state. Right now, see. So if this is a 3-bit counter, if this is a 3-bit down counter, so number of flip-flops are according to the bit you are using. So 3-bit you are using, so it means 3 flip-flops. 1 flip-flop are able to store 1 bit. So 3 flip-flops we are using. Number of states, how many number of states you are going to use? So 2 raised to power n. N is number of bit you are using. So 2 raised to power 3 is 8. Maximum count क्या हो सकते हैं? 2 raised to power n minus 1. So this is for the maximum count. So 2 raised to power 3 minus 1 is 7. So 0 से लेके 7 तक you are able to count with the help of this counter. अब first step है draw the state diagram. State diagram, because it's a down counter, so it is a down counting. So 1, 1 say 1, 1, 0. So with the help of this, you can draw easily the state table in which previous state is this and the next state is this. If I'm at here, the next state is this. If I'm at here, the next state is this. So this is how I'm going to able to draw this table. Now the next step is draw excitation table. Excitation table, we are using JK flip-flop. That's why we draw the excitation table for JK flip-flop. Right. Now, in the excitation table, you know that the 2 inputs are like this. Q1 and the next one is Q1 plus 1. And we find out the value of J and K. So if 0, 0 is here, then this will be 0 and star. It is in a state of holding. If this is previous state is 0 and the next state is 1, then it is 1, don't care. Then this is a set state, or you can say set mode. 1, 0. So if previous state is 1 and the next state is 0, then it would be 0 and 1. Oh sorry, it's a don't care and 1. So this is a reset. And if 1, 1 is here, then this is a don't care and this is 0. This is a toggle. This is a toggling. So this is your second step. You have to draw the excitation table for the required flip-flop. So second step is to draw the JK excitation table of a JK flip-flop. Right. Now the third step. Here I'm writing the third step. Third step is build JK, you can say JK excitation table with the help of present and next state of this state diagram, right? So redraw this table in the next page. Previous state, next state, and this is because we are using 3 flip-flops, then first flip-flop is J2 K2, next one is J1 K1, and the next one is J0 and K0. Okay, so you can see that in the excitation table the inputs are previous state and next state. Here also the inputs are previous state and next state, and you have to find out the values of these. You can easily find it out with the help of excitation table. I'm not write it down here. So So previous states are like 0, 0, 0. Oh sorry, it's a 1, 1, 1 because it's a down counter now. So previous state is 1, 1, 1 and the next state is 1, 1, 0, right? If I might state this here, then the next state is 1, 0, 1. If I might state 1, 0, 1, next state is 1, 0, 0. If I might state 1, 0, 0, this will be 0, 1, 1. If I might state 0, 1, 1, the next state is 0, 1, 0. If I might state 0, 1, 0, the next state is 0, 0, 1. If I might state 0, 0, 1, the next state is 0, 0, 0. If I might state 0, 0, 0, the next state is 1, 1, 1. Now, this is your, just write it down here. This is your key Q0, Q1 and this is your Q2. So what are the values of J2 and K2? Now, the previous state is 1. And here also this is Q0n, Q1n and this is Q2n. Okay. Now, if the previous state is 1 and the next state is also 1. So 1 and 1. Then what are the values of J and K? Don't care and 0. So write it down, don't care and 0. If my previous state is 1 and the next state is 1, then also the same values don't care and 0. If my previous state is 1 and the next state is also 1, so that what are the values of J and K? Same. If my previous state is 1 and the next state is 0, previous state is 1 and the next state is 0, so J and K values don't care and 1. Previous state is 1, next state is 0, so the values are don't care and 1. If my this is over. Okay, now my previous state is 0 and the next state is 0, then the values of J and K is 0 and star. Oh sorry, 0 and don't care. So this is 0 and 0, same value, 0 and don't care, 0 and 0, 0 and 0, 0 don't care, 0 and 1, 0 and 1, 0 and 1. Previous state is 0, next state is 1, then the value of J and K is 1 and don't care, 1 and don't care. Okay, J2 and K2 values are finished. Now we are working on J1 and K1. For that we need Q1 and Q1n. Now in the same way you can fill all the values. So if 1 1 means toggle, so this is star 0, don't care 0. Now 1 0, 1 0 is reset, so don't care 1. Now the again 0 0 means holding, so this is 0, don't care. Now this is 0 and 1, 0 and 1 is 1, don't care. Now 1 and 1 means toggle, so this is don't care and 0. Again 1 and 0 means reset, so don't care and 1. 0 and 0 is holding, so 0 and don't care. And 0 and 1 is set, so 1 and don't care. So this is set. Now to find the values of J0 and K0, you are going to use is the previous state is Q0 and the next state is Q0n. So 1 0, 1 0 means reset, so values are don't care and 1. 0 and 1 means set, so 1 and don't care. Again 1 and 0, 1 and 0 means previous state is 1 and the next state is 0, so it means reset, so don't care and 1. Now the next one is 0 and 1, 0 and 1 means set, so 1 and don't care. And this is 1 and 0, 1 and 0 means reset, so don't care and 1. Again 0 and 1, 0 and 1 means set, so this is 1 and don't care. 1 and 0, 1 and 0 means reset, so it means don't care and 1. And 0 and 1, 0 and 1 is set, so 1 and don't care. So this is the table. Now with the help of table, draw the K map, right? So build K map for each JK input, right? So now the fourth step is build K map for each JK input. So this is your fourth step, right? Now first draw the K map for J2, then K2. So here I am writing the Q1 and Q0, and here I am writing Q2. So this is 0, 0, 0, 1, 1, 1, 1, 0. This is 0 and 1. Now see where J2 is 1. J2 is only 1 when Q2, Q1 and Q0 all are 0. So here the value of J2 is 1. Okay, and you can see that at 0, 0, 1, at 0, 0, 1, this is a don't care. J2 is don't care. So you can combine these two, and this is a one shell, and now the J2 value is Q1 and Q0 complement. Okay, in the same way you can calculate for K2 also. This is Q1, this is Q0, and this is Q2, and this is 0, 1, this is 0, 0, 0, 1, 1, 1, 1, 0. Now see where Q2 value is 1. Q2 value is 1 when, see only the previous state, right, for draw the K map. Now see 0, 0 and 1. So Q2 is 1 is here, and here it is a don't care. So this is a one group. So K2 is equal to again Q1, Q0 whole complement, right? So we find the values on input values of J2 and K2. Now find the input values for J1 and K1. Because we are finding the input value, that's why we are using the previous state to draw the K maps. We are not using the next state. Just remember this. Now what are the values of J1 and K1? In the same way you can calculate. Q1, Q0, 0 and 1, 0, 0, 0, 1, 1, 1, 1, 0. Now see where the J1 is 1, J1 is 1 here and here. Now see the corresponding previous state values here. So this is Q0 and Q1 is 0, 0, but Q2 value is 1. So means here. Now J value is 1 here. Now see the corresponding previous state values. So this is 0, 0, 0. It means here. Right? And you can see that there is a don't care in this shells also. Right? So this is 1, 0. 1, 0, 0 pe. Don't care is there. And 1, 0, 1 pe. 1, 0, 1. 1, 0, 1 pe also don't care is there. So we draw the large group like this. Now the J1 value is equal to, now this is which one is not changing, Q0 is not changing, so Q0 complement is the answer, right? And in the same way you can construct for the K1 also. So like this, Q1 and Q0, and this is Q2. Here also write Q2. Now this is 0, 0, 0, 1, 1, 1, 1, 0, and this is 0, 1. Now search where the values of 1 are, K1 values are 1. So here is, see the corresponding previous state values. So this is 1, 0, 1, 0, 1. So here K value is 1. And in the next one, where the values of K1 is value 1. So here. So this is 1, 0, 0. So here. And you can see that this don't care is present here. So we group like this. Now the K2 value is, K1 value is also Q0 complement. Now the next one is J0 and K0. In the same way you can calculate for the J1 and J0 and K0. Right? Now see, J0 is 1 here, here, here and here. Right? So write it down. And here don't cares are present. So we group the whole and we got J0 is equal to 1. And in the same way you can calculate for K0. Okay, and the k values are present 1 here, 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 and see the corresponding previous state values, so you can find this one. So again we can group the whole, and the k naught value is equal to 1. Now I'm just going to highlight all the values, input values. So J2 is K1 and K2 complement, Q1 and Q0 complement. So J2 value is equal to K2 value. Now J1 is Q0 complement, K1 is also Q0 complement, so these are the equals. Now J0 is 1 and K0 is also 1, so it is also equal to. Now see, what is the correct option? So correct option is J0 and K0 value is 1. Yes, it's not 0, it's 1. We calculate it. Now the next is J1 and K1 is equal to Q complement, Q0 complement. Yes, it is correct. We have calculated J1 and K1 value, input value is Q0 complement. And the J2 and K2 is Q1 complement and Q0 complement. J2 and K2 is Q1 and Q0 complement. So sixth one is also correct. So fourth is the correct option. Second, fourth and sixth are the correct one. And you can also draw the the whole 3-bit synchronous counter with the help of this input, right? So there's no spaces here. So if this is a J0 and this is your K0, this is Q0 and this is Q0 complement. Now the initial values of J0 and K0 is 1. So we give the logic 1 here, right? And this is a synchronous counter, so it means all the for every flip-flops clock is same. So the next flip-flop is J1 and K1. This is Q1 and this one is Q1 complement. And what is the input for this J1 and K1 is, we have calculate is Q0 complement. So Q0 complement value given to this J1 and K1, and this is the output Q0. It gives you the output Q0 0. And this is a synchronous counter, so the clock will be same for all the flip-flops. Now the next one is J2 and K2, and this one is Q2 and this one is Q2 complement. This will be your next output. What will be the inputs for J2 and K2? You calculated Q1 complement and Q0 complement. So Q1 complement here. So we are using the AND operation here and gate here. So Q1 complement go here and Q0 complement like this, and the resultant given to this to J2 and K2, and the output will be Q2. So this is the whole, you can say, this 3-bit down counter, synchronous down counter, right? It's look like this. Now the next question is question number 9. Convert the octal number. So this is the octal number 0.4051 into its equivalent decimal number. So the decimal equivalent is equal to 0.4 into, because these values are from right hand side of the decimal, so we are writing 8 power minus 1 plus 5 into, this is for 2, this is for 3, and this is for 2, for 4. So 5 into 8 power minus 3. And the next one is 1 into 8 power minus 4. And this is a decimal equivalent. So the base is 10. Now after solving this, you got something 0.510000976 and something, right? And if you take the approximation, so this is 5100097, and because the number is after 7 is greater than 5, so this will be this is 978. So after approximation you got this answer, so that's why option A is the correct one. Now the question number 10 is the hexadecimal equivalent to the octal number is, so this is your octal number, so it means the base is 8 and we represent each digit with the help of 3 bits. In the octal representation we represent each digit with 3 bits, and in the hexadecimal mein each digit represent with 4 bits. Okay, now see, so write it down from here. So 7, how are you going to represent 7 with the help of 3 bits? Like this. Now 5, how are you going to represent 5 with the help of 3 digits? So this is 4 plus 1, 5, 3 is 0, 1, 1, and 2 is 0, 1, 0. Now we want to represent this number in hexadecimal. So for that I need to group 4 bits together, because in the hexadecimal I represent one or you can say one digit with the help of 4 bits. So start grouping from this side, from left to right. Now 4, 1, 2, 3, 4, right? So this is 4, 8 plus 4 is 12, 12 plus 2 is 14, 14 plus 1 is 15, and 15 is, so you can say that 0 to 9 number is here. Now 10, 11, 12, 13, 14, 15. So 10 represent in hexadecimal is A, 11 represent B, 12 represent C, 13 represent D, and 14 represent E, and 15 represent F. So the number is 15, so it means this is F. Now this is 8 plus 4 is 12, 12 plus 2 is 14, so 14 represent by E. So this is E, and this one is 4. So 4EF is the hexadecimal representation of this number. So third is the answer. Now question number 11 is, which of the following cannot be passed to a function in C++? First is constant, we can easily pass it. Second is structure, we can pass. Third is array, we can pass. But fourth is header files. We are not passed header functions, or you can say header files, in a C++ function. So fourth is the answer. So it's very simple. Now the question number 12 is, which one of the following is correct for overloaded functions in C++? Overloaded functions. So option 1 is compiler sets up a separate function for every definition of function. Option 2 is compiler does not set up a separate function for every definition of function. Third is overloaded functions cannot handle different types of objects. And the fourth one is overloaded functions cannot have the same number of arguments. Now first understand what is overloaded function in C++. So the thing is function overloading. What do you understand by function overloading? You know that in a program there are so many functions are present. But sometimes it will be a case that two functions have same name, right? But the argument present in the functions are different, right? So if you can say if more than one functions are present in your program with same name, but they are they have different arguments, then you can say that it's a function overloading. In the function overloading, two or more functions with same name but they have different arguments, right? So this is a function overloading. Now they ask the question that if function overloading is present in your program, then which condition holds true for that? Okay, so whenever you can say that whenever you call the overloaded functions, right, so compiler determines the most appropriate definition to use by comparing the argument types you use to call the function. Because different function calls are there in your program, different function calls are present with the same name but the arguments are different. Let's suppose two functions like void sum, int xi, int x2, and in somewhere in the same program some another function is there, the name of the function is same but the arguments are different, like float xi, or you can say I1 and float j2. So this is a function overloading because the name of the function is same, but the arguments we are giving. In this case, the arguments are integer types, but in this, the float type, you can say the float type arguments are we are given. So the compiler duty is the compiler finds, or you can say the compiler determines the most appropriate definition of a function to use. You can say to use the different type of arguments, because here the arguments are float, here the arguments are integer. So according to the requirement, the compiler going to choose which one is the best match. Now see the options one by one. So start from the bottom to up. Overloaded functions cannot have same number of arguments. They can have. It's not mandatory that they cannot have the same number of arguments. So this is wrong. Overloaded function cannot handle different type of objects. Yes, it can hold the different type of objects. So it's also wrong. Compiler does not set up a separate function for every definition of function. No, it's not true. The reason is here we also explained that if we have different functions with same name but different arguments are present, so according to the best match, compiler will decide which will going to use between all these functions. So compiler, in this case, the compiler set up a separate function for every definition, because the different definitions are there. So it set up a separate function for every definition of a function which is available in your program. So option 1 is the correct one. Now, which one of the following storage classes have global visibility in C and C++?